Hey, um, this, ah, yeah, come on. Can you hear me all right? Perfect. Okay, I'll quickly rush through two, maybe sort of three topics. But as I'm here in front of reflectivity experts, I think I can get away with it. And the first reason why I thought it would be nice if I could show you the fastest XRR curve you've hopefully seen in your life. If you've seen a faster one, I'd like to know, and I would be probably sad. Um, it's just a test experiment, but I think it's still neat. And if you are not interested in super fast X-ray reflectivity, then I think at least some of the implications from this that you get a lot of data may be relevant for more and more of us. And artificial intelligence fits of big data sets are, I think, one way forward. And I'm very happy about the previous talk because it fits perfectly in with the very last thing I want to show, reinforcement learning in a slightly different way as previously shown. So let me quickly go through this. So I'll show you some quick XRR leading to large data. Large data, I'm talking about hundreds of thousands of XRR curves. You maybe don't want to refine with a slow tool. If you have so many curves, you should think about co-refinement and in the end, maybe even think about letting an AI decide what to measure. In reflectometry, I know in neutron time of flight measurements, you can leave your sample still, but in monochromatic X-ray experiments, you need to move your sample to get different angles of incidence. And that's tricky. But one thing we can do is at least let the detector stand still. So we need to move the sample back and forth, and since the reflected beam moves up and down. So this is tricky. We have to move this fast if we want to get fast, but at least the detector can stand still. And we need attenuators, which we again put in front of the detector in the setup and leave still for the experiment. And then you get I'll show you two ways: either rotate the sample quickly and have it on a slight wedge, or to scan it quickly with a Galvo scanner. And if you rotate with these absorber steps, you get a curve like this. And if you set it together, you get out your nice X-ray reflectivity curve. And I'll show you 1.4 milliseconds is the limit for this rotating sample and 270 microseconds for full resolution X-ray curve is what you can do with the other Galvo scanner. Just to illustrate the rotation of something like this, it's 0-degree incidence, and in the beginning it's a larger angle of incidence, and we just let it rotate all the way around, and then the incident angle periodically changes. And a rotating sample fits perfectly to spin coating, so that's what we did as a first quick XRR example, spin coating of PMMA, which has been studied with optical interferometry a lot. But of course, X-ray reflectivity is better in getting both the refractive index and the thickness independently. And I don't want to get into the details. It's published work by now. In the beginning, you see no reflectivity. Even the edge disappears when the droplet hits your substrate. But then after a while, the edge reappears. And the film very quickly in spin coating forms this nice layer. And you can fit all of these quick XRR curves with a neural network and extract things like the thickness evolution. And you get fairly fast time constants in the 20 to 70, 20 to 80 millisecond range, how quickly the film spreads and thins out. Again, I don't want to get into the details of the system, but these are sort of 10 millisecond XRR curves. And we wanted to get faster, so we found this thing here, which is from laser shows or 3D printers, metal 3D printers for beam steering a laser. And instead of having a laser mirror in front here, we attached our sample. And then this motor can incredibly quickly at 2 kilohertz shake your sample back and forth. And that's what's shown here. So that's the incident angle, and the motor moves the sample to a steeper angle and then moves it back. But you can already see when we wiggle it very quickly with a triangle, you see slight wobbles. So we have to be now a bit careful and take the derivatives. That's the speed of the motor, or the angular speed of the sample. And we see the speed is actually not constant, and that varies the integration time on different pixels. So we need to correct for the speed or conversely probability density of the beam being there. And we do this correction. That's our detector image. That's our signal from the region of interest. And now the green dots are extracted from this image, and the blue curves is a normal detector scan. And it fits quite well, and that's now for 1,000 microseconds or 1 millisecond, but we can go faster. So that's now 500 microseconds. You see it's getting a bit noisy, but we fit these green dots and they still give the same answer. And you see the Kiesig oscillations. And that's now 263 microseconds for the full scan. And again, you still see the fringes, but now it's really pushing it. And I'm happy because in a lot of experiments, I did not use the ESF, or in this case, it's done at Petrosine in Hamburg to the fullest. But here I really used it to the fullest because out here, we are limited by the photon flux of the synchrotrons. We start with 10 to the 12. The reflectivity has dropped by 10 to the 5. In 263 nanoseconds, on each pixel, the beam is only or each pixel only sees the beam for 263 nanoseconds. So in total, only 2 to 3 photons from our primary beam are left on this side. And then it's also noisy over here, which is even sadder. So here we want a better synchrotron. Here we want a better detector because the beam is on the pixel for so short, and single photon counting detectors can only count for so many pixels, that we need to put in loads of absorber over here, even though we would have plenty of photons, because the detector can't count them away in a very short time. So I'm happy that we managed to really get to the limit of current technology. And now we want, of course, better detectors, which are not yet available. So integrating the detectors would be the way forward, as they have on the XFEL sources. They're usually not available on the Good. That was the first thing I just wanted to show what I think the current limit. And if you acquire a curve every millisecond, you get 60,000 XRR curves per minute. And we have tens of thousands, over the total experiments, hundreds of thousands of XRR curves, which for us was a bit of a new challenge, starting with fitting the single curves, 10 curves, but 100,000 is a lot. And I was completely shocked when I spoke to Thomas Sabeck here, because I always thought neutrons are slow. And then he showed me this curve, a 60 millisecond neutron reflectivity curve, and he said that 1995, this was an 8-hour experiment. That's what my prejudice is, that neutron scatterers are gentlemen scientists who go skiing in Alpe d'Huez. But no, they are getting fast as well. So I think the natural way for any technique is to get faster, better, more data. And so it's a general trend of maybe analyzing this data quickly is common for many of us. And so that's the point where with Frank Schreiber's group, we have been pushing machine learning for analysis for quite some time now. And one side effect is that the machine learning predictions are fast, and we can predict a lot of curves. But I also want to stress that maybe they're even better than what we have so far. So what's plotted here is a genetic algorithm fit with RefNX, but doesn't matter which package you use. And that's the true thickness. These were simulated curves. And that's the predicted thickness. And most of the time it works beautifully, but every now and then you have some outliers. It's just not converging properly, or it's ambiguous and it's not converging. precisely. And that's what our neural network spits out. And you see there are a lot less outliers because the neural network has seen the whole parameter space during training and is less likely to get lost in some side minimum. Apart from being a lot faster in predicting one curve, which for tens of thousands of curves makes a difference, I think it might also be the new state of the art of accuracy. And yeah, that's the first paper, but there have been many more papers you've heard about ML Reflect in the session. And there are lots of different analysis tools. And I think that's why ORSO is very important, that we all talk to each other. And I hope that we get to a state where maybe some of these tools, at least from a user perspective, I can drive a car from different brands without needing a new driver's license. And similarly, under the hood, they may have similar motors, electronics, that maybe we can also get a little bit in the directions that we can maybe more easily use different packages. There will always be the need for different cars or different packages. And but yeah, I think also is very important for file formats, model language, getting maybe a little bit of synergy from different approaches. And hopefully machine learning fits in here as well in the future. We heard just before that if you have a time series, you can do co-refinement with or without reinforcement learning. We've also looked at this with a slightly different approach. So all the individual curves can be assembled to a 3D plot or 2D density map. And it's not the best way to analyze them one by one, but if you have the whole queue and time dependence, then it's really nice to fit the whole thing because it belongs together. And I unfortunately don't have time to get into the details, but we can reparameterize the whole problem in the language of a growth model, some differential equations, which are describing a huge variety of different sample classes and how they evolve in time. And then what we do is we fit with either a neural network, a convolutional in this time case, or with RefNX, thanks to the help of Andrew Nelson, these parameters, not the roughness, thickness, density, but we fit some growth rate and roughening exponents and stuff like that. And the good thing is, here you see the experiment. Here you see the fit of individual curves, and you see our experiment had some noise here. And the individual curves reproduce the noise, even though it's not real. So that's not a good feature. And our growth model regularizes this. Either doesn't matter whether we co-refine with RefNX or with a neural network. And so that is nice to refine all of these curves at once, because the growth physics is included and you are not set off by a bit of noise in your data. And once you do this co-refinement, quite interesting results happen. You can, for example, sample a lot more sparsely. So that's probably a bit too extreme. But if you plot the error of the thickness prediction as a function of how sparse you sample, so if you go left, you can measure faster and sample less. And the individual curve fit takes off a lot earlier than either RefNX or the CNN model. They behave pretty similar. And you can get an order of magnitude lower points, and neural networks, and again, also co-refinement are also very noise tolerant. So you can still measure all points depending on your technique, but just measure with fewer counts and worse statistics. And again, the error in the thickness prediction goes up very quickly if you add noise and fit individually, but the total data set, if you co-refine it, you can have a lot noisier data before the error starts to be significant. That's thickness, density, and roughness. And for all of them, you see that both RefNX and the convolutional neural network are a lot more noise tolerant because they have prior information about the growth and they get the whole data set, not individual code. Okay, I'll skip this and come to my last point. It's nice if we measure fast, but is it possible to let some neural network decide on the measurement strategy and maybe save some dose on the sample or measure more accurately? And some years ago, Google solved these Pac-Man Space Invader-like games by letting some artificial intelligence with reinforcement learn to play it. And luckily, you've just heard before how it works. You have an agent which can interact with some system. And here, the agent knows that it should increase the high score and not die. And all it knows it should increase the high score. Yeah. And then slowly by slowly, it learns how to play this thing. And self-driving cars are another example of this reinforcement learning class. And so my goal is now a self-driving diffractometer. And how should this work? I may usually measure lots of points in one X-ray curve. If I measure only 32 points instead of all of these, this curve is maybe not fittable anymore. But if I choose my 32 points wisely, it might be a fittable curve. That's just the concept. This is a hard problem to formulate as an optimization problem. That's why we try this reinforcement learning. But there are also, we just before discussed Hogben code by Josh Cooper. So there are many ideas, and this is also in its early stages. But one advantage here is that the neural network measures the point and decides on the next. So it's continually thinking and adaptively scanning. So you don't have to decide in advance what you want to do, but while it's scanning, it's thinking about it and analyzing. And you've seen this before, so it can be quick. An agent can do an action. For us, that's where to measure and for how long. So our actions are you can measure at any of these Q points, and you can measure an arbitrary number of times at a given Q space. So we are changing the Q points, and we are changing the integration time. And then the action is what the diffractometer gives back to you as a count rate. We fit this partial reflectivity curve, and depending on how close we are to the real parameters, we give it a reward, and it can measure somewhere else and goes in circles. And there are some details about the reward function. You want to minimize the error, and it should be stable, and we should encourage exploration in the beginning, so that it doesn't. In the beginning, our artificial intelligence was mostly artificial stupidity, always measuring at the same point. But it gets better, so I'm skipping this a little bit. One trick is that we simulate our X-ray machine, so we can do loads of experiments and do this quickly. I'll show you the results. So these are the errors we get if we measure 32 equidistant points or 256 equidistant points. Here our agent starts to learn and measures. Now we let it move until it measured 32 points. And in the beginning, it's pretty dumb and measures 32 points, which yield a high error when you fit those 32 points. But then it gets smarter and smarter and smarter. And in the end, it learned to measure 32 optimal points. And if you fit those points, actually the error in the parameters is better than if you fit 128 points. So this optimized AI agent can be 4 times faster or more than 4 times faster than just doing equidistant scans like, I guess, a lot of X-ray people. And we've looked at this equidistant scan, and the agent was allowed to control our X-ray machine. And 64 equidistant points in this case yielded a fairly bad result compared to the true, but the agent got very close. Okay, with this I want to stop. So we were quite quick in XRR in the last 2 years. there are large data. Synchrotrons are amongst the largest data producers in the world, but I guess neutrons are also getting fast. Machine learning is fast for analysis, which is important for these large data sets, and potentially it's even better than what we have currently. Co-refinement of these data sets helps, and we can get 4 times faster if we do adaptive scanning. Thank you.